Hey guys, so in this video I'm going to do 8 different examples of L'Hopital's rule. So this video will show even more examples than what I did in my 4-part lesson series. And I assume that you got the basic idea of how to approach L'Hopital's rule, but wanted more examples if you're watching this video. So if you haven't watched the lesson videos and want a slower breakdown of the concepts that I'm going to talk about in this video, I highly recommend that you go back and check out the lesson videos, because these, I'm just going to assume, like I said, that you kind of know what I'm already talking about. So I will have links to all of those videos in the description. And then, by the way, I'm doing 8 problems here. If you just want to see the entire problem set, you can go to divideandconquermath.com and then you can get the free guided notes. So we're talking about L'Hopital's rule. So I'm just kind of showing you here, so the actual statement of L'Hopital's rule. So this is something you should already be familiar with, as well as how L'Hopital's rule applies to these different indeterminate forms. And this is something I've broken down throughout the course of my lesson series. So in this video, I'm going to go through I'm going to show you all the examples. And of course, if you want to use this as a way to quiz yourself, you can always pause the video. I really think that this particular set of lessons, or this particular set of examples, is best done with having the guided notes with you. But again, you can pause and you can do whatever you want with this video. If there's a particular example that you want to see, you can just go right to that. Okay, so let's jump into this then. So starting with the first example. So the first thing that I really need to know here is, what indeterminate form am I dealing with? And so just notice, if I were to try to plug in 0, I'm going to get 0 over 0. So this is really like our classic L'Hopital's rule. And so what that means then is I can go ahead and take the derivative of the top and the bottom. So taking the derivative of the top, notice I am going to have to use the chain rule here. So that's going to be cosine of x squared times 2x. And in case you weren't sure, so this is different from sine squared x. So if this were sine squared x, that would mean the entire sine function is being squared, but that's not what we mean here. We mean that the x is being squared. Okay, so there's the derivative of the top, and oops. And now the derivative of the bottom is just 1. So looking at what I'm left with, I've got 2x times cosine of x squared. So what happens if I plug 0 into this? Well, now I'll get 2 times 0 times cosine of 0, which is just going to be 2 times 0 times 1. So this will just equal 0. And so there we go. We're good to go. Okay, so moving on to the next example here. So once again, you always want to kind of figure out what is it that you're dealing with here. So if I try to plug in this limit as x goes to negative pi over 3, I've got 3x plus pi over sine x plus pi over 3. So let's just see what happens here. So if I try to actually plug this in, so I get 3 times negative pi over 3 plus pi, and then in the denominator I get sine of negative pi over 3 plus pi over 3. And so this is going to give me negative pi plus pi over sine of 0, which is again 0 over 0. So we've got just good old classic L'Hopital's rule here. So I can get rid of all this stuff. And now I can take the derivative of the top and bottom. So notice I continue to write my limit notation. It's negative pi over 3. I'll write that a little more clearly. So taking the derivative of the top will just be 3. And then let's see, taking the derivative of the bottom, so I got to use the chain rule here. So this will be cosine of x plus pi over 3, and then the derivative of the inside would just be 1, so I guess that really didn't do anything. Okay, so now let's see what happens if I take the limit of this. So the limit of the top function will just be 3, and then I can really just plug in negative pi over 3. So this is going to give me 3 over cosine of negative pi over 3 plus pi over 3. So this is 3 over cosine of 0, which is going to be 3 over 1, which just equals 3. And so that'll be our answer. Okay, so moving on to the next one. So now let's see what happens here. Again, if I just try to plug in 0, well, what I'm going to get is 1/3 to the 0 minus 1 over 0. And this is ultimately going to give me 0 over 0. So I've got another classic L'Hopital's rule. So I can start here by taking the derivative of the top and the bottom. So this is going to be 1/3 x times the natural log of 1/3 now over just 1. And this I can definitely take the limit of now. So I got rid of that 0 over 0 problem. So I can just go ahead and actually plug 0 into this. And anything to the 0 power is 1. So this is just going to be the natural log of 3, and we're done. Oh, sorry, I said 3, I meant 1/3. Okay, so moving on to this next one. So in looking at this, notice that as x goes to infinity, this x squared is going to go to infinity, and then this x to the negative x is going to go to 0. So this is one of our indeterminate forms, but I talked about in video 2 how when you get this form, you now have to manipulate this type of expression so that you can actually use L'Hopital's rule. Now, in this case, there's actually some low-hanging fruit as far as manipulations go. I could just rewrite this expression without the negative exponent. So let's see if that's enough to help me. So I get x squared over now e to the x. And so now look what happens if I try to evaluate this as x goes to infinity. Now instead what I get is infinity over infinity, and that is one of our indeterminate forms where we can just go ahead now and actually take the derivative of the top and the bottom. So I'm going to go ahead and do that. So in the top I have 2x, and then the bottom I still just have e to the x. Now notice as x goes to infinity, I still have infinity over infinity, but that is okay. I can just take another derivative, so that's what I'm going to do. All right, so taking one more derivative, I've got the limit as x approaches infinity of 2 over e to the x. Now in this case, I no longer get infinity over infinity. Instead, I get that this is going to infinity in the denominator, and we know that when the denominator is going to infinity, the entire expression is going to 0. So now I finally have a definitive answer. It's 0. Okay, so moving on to this next problem. So once again, if I just take a look at what happens as x approaches 1 on the right, so this expression here is going to go to positive infinity, as is this expression. They're both actually going to go to infinity. So what you're left with is infinity minus infinity, which is another indeterminate form. Now, I talked about in video 2 kind of different ways of how to deal with this, but in this case, since these are both fractions, I probably want to see what happens if I get a common denominator and just reevaluate the whole situation. So if I want to do that, then what I'm going to do is this is going to be the natural log of x over x minus 1 times the natural log of x minus x minus 1 over x minus 1 times the natural log of x. So I'm working towards getting to my common denominator. So just be careful when you actually combine these fractions. Oops, so this is the limit as x approaches 1 on the right. So now this is going to be the natural log of x minus x minus 1 over that common denominator. And just another reminder, the point of this is to get like this all is one solid expression. You don't want to start canceling things out. And also it would be wrong to cancel out natural log of x and natural log of x. That's not a legal cancellation in this case. So if I work this out as far as I can, this will be the natural log of x minus x plus 1 over x minus 1 times the natural log of x. So now let's see what I get. So now if I try to actually, put in 1, the natural log of 1 is 0, and then this will be minus 1 plus 1. So the top here is 0, and then the bottom here will also end up being 0. So I have 0 over 0, so actually now I've put this into that classic L'Hopital's rule form. And so now I can just use L'Hopital's rule. So let me clear some space. And now let's take a derivative. So taking the derivative of the top, this is going to be 1 over x minus 1. And then taking the derivative of the bottom, so now I got to use the product rule here. So taking the derivative of x minus 1 is just going to be 1 times the natural log of x, plus, now I leave x minus 1 alone, and then multiply that by the natural log of x, by the derivative of the natural log of x, which is 1 over x. Okay, so let's see. Let's clean some of this up. So I've got the limit now as x approaches 1 on the right of 1 over x minus 1 over the natural log of x plus 1 minus 1 over x. And okay, so now let's see if I can just go ahead and evaluate what's going on with the limit here. So as x goes to 1, now this is going to go to just 1, as is this. And then the natural log of x, this is still going to go to 0. So now if I just do the math here, so I get 1 minus 1 over 0 plus 1 minus 1. So I still get 0 over 0. So that's okay, but we just had to take a second to figure that out. So I guess we're going to have to take another derivative. So let me clear some space. And let's do it again. So I've got the limit as x approaches 1 on the right. So taking the derivative now at the top, this is going to be negative x to the negative second over, let's see, the natural log of 1 over x is the same as x to the negative 1. So I want to just stay consistent here for a second. And then plus x to the negative second. So here's what I have now. All right. So now if I were to plug in 1 for all of these, let's see what happens now. So on top, I'm going to get negative 1, and then in bottom, I'm going to get 1 plus 1. So this is going to equal negative 1/2. Okay, and now we're good to go here. Okay, so moving on to f here. So again, just taking a second to recognize what indeterminate form do we have. So I've got the limit as x approaches infinity of the natural log of x to the 1 over x. So the natural log is just, as x goes to infinity, is going to go to infinity. But this exponent is going to go to 0. So this is one of our indeterminate forms, infinity to the 0. So I broke down in the third video how to approach problems like this. So I'm going to go just straight into using the approach. So if you have no idea what I'm talking about, I highly recommend that you go back to the third video in this series. So what we talked about in that video was taking the natural log of this whole expression. So if I take the natural log of all of this, then what I can do is I can take this exponent and bring it down in front. So let's start by doing that. So I bring down the 1 over x. I've got the natural log of x. And one thing I want to address just before I go any farther, so some people might think, why couldn't I have just brought the 1 over x down right from the onset? So this 1 over x actually applies to the entire expression. It's not like, so if I had something like, let's say, the natural log of x to the third, this 3 is applying to this x, and so then that's where I can use the power rule to bring this down, to make this 3 times the natural log of x. But that's not what we have here. I have all of this natural log of x to the 1 over x, so this does not apply to this, so I can't use the power rule here. So I just wanted to really quickly address that in case somebody looked at this and thought, hey, why do we have to do this? Okay, so now that I have this written like this, so notice that I still have like an indeterminate form that I can't really use, because this will give me, this is going to go to 0, and now this is going to still go to infinity, but I can now rearrange the terms. So I'm going to make this now the limit as x approaches infinity of the natural log of x over x. And now look what's happening. The top is going to infinity and the bottom is going to infinity in how I've rewritten this. And so now that I have that infinity over infinity form, this is when I can actually go ahead and take the derivative of the top and bottom. So let's do that. So I've got the limit as x approaches infinity of 1 over the natural log of x times 1 over x. That's the derivative of the top, and then the derivative of the bottom is just 1. Okay, and so now if I rewrite all of this, I've got the limit as x approaches infinity of 1 over x times the natural log of x. Well, now just the entire denominator is going to infinity. The top will stay as 1, so then this whole expression is just going to end up going to 0. But now that we have 0, so now you have to remember, we're not done. So right, we started off by taking the natural log. So now I want to just remind you of kind of what the procedure is here. So after you take that natural log, then you're actually going to be leveraging this property to help you finish off this particular limit. So I have this kind of set up. I know what this limit equals 0. So let me clear this all off. And now what I want to do, so I want to treat this as my f of x, and I'm going to restate that property. And again, I went through this in great detail in video 3, which is why I'm kind of going through this at a quicker pace now. So if you feel like you want to see more explanation on this, check out my 3rd video in the series. Okay, so I've got the limit now as x approaches infinity of f of x. This I know is equal to the limit as x approaches infinity of e to the natural log of f of x, and this is the limit that we just determined. So now I can just jump right ahead and say that this is going to equal e to the 0, and anything to the 0 power equals 1. So that is our limit. Okay, so moving on to g here, so we have very much the same problem that we had in the last one. This gives me 0 to the 0, so I know that I'm going to have to use that same trick from before. So once again, I'll start off by just taking the natural log of this guy here. So I've got the limit then as x approaches 0 from the right of x times the natural log of x. I just went ahead and brought that power down. And you'll notice in this particular problem that we have another problem. This is going to 0, and the natural log from the right is going to end up going to infinity. So now I've got 0 times infinity. So now I've got to, this is a different indeterminate form, so now I got to, put my thinking cap back on. And so this is a trick that I talked about in video 2 that we're going to use again. It's that I can rewrite x as the same as 1 over x, or that's the same as 1 over x to the negative 1. So this is the way that I would prefer to think about this now. So I'm going to make this little manipulation. So with the limit as x approaches 0 on the right, I'm going to leave the natural log on top. And for right now, what I want to do, I want to think about this as 1 over x. Because what happens now is, now if I think about what happens as the limit approaches 0 on the right, this is still going to infinity, but now so is this little fraction. So now I've actually turned this into the indeterminate form of infinity over infinity. And once you get that particular form, then you can use L'Hopital's rule and take the derivative of the top and the bottom. So now we are kind of in business, if you will. So the derivative of the top is 1 over x, and then the derivative of the bottom is going to be negative x to the negative second. Okay, so now what I want to do is I want to just rearrange all of this and take a second to clean up how this looks. So let's see. I've now got x squared, this is negative x squared, over x, and this is still approaching 0 on the right. So this is the limit then as x approaches 0 on the right. This is ultimately going to simplify to just negative x. So finally I can evaluate this limit, and this just equals 0. But wait, we're not done. So don't forget, this all started because we took this natural log. So now I still have to leverage this property here to finish this off. So if this were me, because I kind of have the memory of a hamster sometimes, like going through all this, I feel like I would be very likely to just be like, oh, it's 0, and then I'm good to go. So if you find that you forget to finish the problem, consider writing yourself like a big note when you're doing these so that you don't forget. It's something you got to try to break yourself of, or find some habit to have when you do these types of problems. Okay, so let me clear this all off. And now from the top, let's think of this as my f of x. So I'm going to leverage that property. So the limit as x approaches 0 on the right of f of x is going to be equal to the limit as x approaches 0 from the right of e to the natural log of f of x. And this is what we just figured out. So now I can just plug in the limit. So this is going to equal e to the 0. So once again, this just equals 1. And now we are done. Okay, and now for this last example here. So notice that this is going to give me the classic 0 over 0 form. So I've got the limit as x approaches 0 on the right, square root of x over the square root of sine x. So I want to go ahead and take the derivative of the top and the bottom. All right, so this is going to give me 1/2 x to the negative 1/2 on top, and then in bottom this is going to be 1/2 sine of x to the negative 1/2 times cosine of x, because I've got to use chain rule there. Okay, so if I try to simplify all of this, this is going to turn into the limit as x approaches 0 on the right of the sine of x to the 1/2 over now x to the 1/2 cosine of x. All right, so you want to think critically every time you take these derivatives. Ideally, what should be happening after you've taken the derivatives and you've simplified and everything, you should see like an end in sight. Like if you have to continue to take derivatives, there should be like some progress. Notice that after taking this first derivative, I'm almost back to where I started, but now I have an extra cosine x in here. So this is not progress, but you know, let's take one more derivative and see what happens. So let me clear some space. And so I still get really 0 over 0 here. So I can use L'Hopital's rule again. So if I take the derivative of the top, this will be 1/2 sine of x to the negative 1/2 times cosine of x. And then in the bottom, this will be, now I'm going to use the product rule here. So this is going to be 1/2 x to the negative 1/2 cosine of x plus, minus x to the 1/2 sine of x. And now this is just a bigger mess, right? This is even worse than where we started. So I can see now that if I just keep taking derivatives, this is just going to get bigger and bigger. This is just going to kind of spiral out, and we're not going to drop any x's, which is kind of the hope when you're taking derivatives. So what that tells me is that this is one of those cases where L'Hopital's rule it doesn't really work, in that the derivatives just keep cycling. So we can't really use L'Hopital's rule. So we're going to have to think of something else. So let me clear this all off. And now we got to get pretty darn clever. So here's what I'm going to do. I'm going to take this square root. Notice this is x over sine of x. And actually, this should look very familiar to really one of my favorite things from limits. This is actually related to an old theorem that says that the limit as x approaches 0 of sine of x over x equals 1. Well, this actually works in both directions. You can also have this as x over sine of x. So either way, it still works actually. So this whole thing, I have to really just rely on this little fact here. So I know this is going to 1. So this whole limit then is going to equal the square root of 1, which equals 1. So I didn't even really need L'Hopital's rule if I just knew this favorite limit of ours. And so that is it for this video. So hopefully this was helpful. If it was, please consider leaving me a like or hitting the subscribe button. And if you have any questions, you can always drop me a comment. I'm always looking for new ideas, so anytime you guys give me any feedback, positive or negative, or even questions, it generates new ideas for things I can add to my channel. Thanks for watching, guys. I'll catch you next time.